Okay, so what did we talk about last time? We're right in blue. Now, okay, we started talking about our model system of particle on a ring. If we're looking at this thing in a sort of 2D plane, we had X and Y. What did we say about the path of the particle, or the quantum particle? Yeah, it's moving around in a fixed distance, right? And what was that distance? Yep, r. So it's traveling around that ring at some distance r. Ellen, you said something about arbitrariness. Yeah, we said the potential energy is arbitrary. So there is a constant value it could have. It doesn't really matter what that value is. So what did we set the value equal to? 0. Yeah. And why would you do that? Yeah, exactly. So you don't have to add like -2 to everything you're doing. Okay. So we set up our particle system. What else did we do? Yep. We need phi in here. And that was the degree somewhere in there. It really doesn't matter exactly where it is because these coordinate systems are arbitrary. What else did we do last class? Yep, we found angular momentum in what? We did do that, and what did we apply that or put that into, I guess is my question. Yep, so we had our generic Schrodinger equation, and we got to a point where we could have utilized that equation. But we also said that was equal to right? And you're right, Lily, we said, hey, angular momentum somewhere in here, which we're going to draw upon several times as we go through here. The other thing we did, normally what type of coordinate system do we work in or have we worked in so far? Yep, we've normally worked in Cartesian coordinates, but what did we move to, Will? Yeah, exactly. So we moved to spherical polar coordinates. We went through a demonstration of that, right? Okay, so now we're here. We have a Schrodinger equation. In all of our other systems, what did we do next? Yeah, we got to figure out what the wave function is. So let's try to determine in this class what is the wave function for a particle on a ring. Sorry, this is like way bigger title than what I wanted. Big chalk. It is fun when the weather gets warm. I used to try and do PChem out front here on the ground, and it just never worked. If we have the big rolly board, we might try it sometime then. That's fun. It's so much better outside, except when they start mowing the lawns, then it's awful. Okay, so we got particle on a ring. We got to determine psi. So how are we going to figure out what the wave function is? What equation are we going to utilize? Or what have we done in the past to figure out psi? Do we have an equation that psi must obey? Any equation at all? Hey, yeah, the Schrodinger equation. That's why we spent the time on it. Okay, so we're going to utilize that to figure out our psi. We could go operate with either one of these. I want to go with this guy. So phi squared psi is equal to E psi. Okay. Right now, does this look like an eigenvalue eigenfunction relationship? Not really. We can manipulate this around to get a little bit better. What does a generic relationship look like? Yeah, we'll go with operator O operates on wave function. What do we get out in the end? Yep, times what? Yep, that wave function back. Okay, so we gotta try to make it look like this. What could our operator be in this case for our particle on a ring? Yeah, we'll just use that second derivative as the operator. Okay, what do we want to do with this bit over here then? Yeah, so what would you do with it? I'm sorry, I couldn't hear what you said. That's okay. Yeah, let's move it to the other side. that's what I thought you initially said. I just couldn't hear you. And unfortunately, I have bad sinuses, so I had to go to the sinus doctor, and I thought I was losing my hearing, but they pushed pressure on my ear, and now I can hear perfectly out of this ear. That was right before the hearing test. So they're like, no, you have impeccable hearing. I'm like, I swear I couldn't hear out of that ear the other day. Anyways, sorry. I can't stop with story time today. You can tell we're close to break. Okay, let's move all the other stuff over to the other side. So we get E. What else do we have here? Yep. Times what? Yep, wave function. Okay, does that look like an eigenfunction eigenvalue relationship? Yeah. Okay, Lily, you already told me what all this junk was. What's all that? It's all a constant. Okay, so we can define, even the sound of this chalk sucks. We're going to define it this way. We could just conglomerate everything as K in here, but trust me, it's just going to make the math work easier in a bit. Okay. So we have some function. We take two derivatives or the second derivative with respect to the only parameter in it, and we end up with a constant in this guy. We might know a couple of solutions to this one. Yeah, we'll just do equation. What type of mathematical functions do you know that could work where you take two derivatives of them, or second derivative of it, you end up with some constant in that same function back out? Yeah, sine we could go with. What else? Cosine. Yeah, and what's their third option? Yeah, e to the something. We could elect to pick any of those because they're all actually all connected through Euler's theorem. But what we're going to select is e to the something. So we have our wave function. What is the only parameter that our wave function depends on? Yep. We're going to do a times e to the I k v. Okay. That one will work out fine. I, imaginary I, k, we've defined that constant kind of up here. What's this thingy, A? Yep, that's a normalization constant. Okay. What do you think we're going to do next? We're going to find A. Before we do that, though, we have to determine the bounds of our system. And we have to make sure, one, our wave function's continuous from the postulates of quantum mechanics. So let's consider some bounds. Try this one. I don't really like that color, but this chalk feels good. So. Okay. Our system's traveling on a what? A ring, circle, right? How unique is this circle? So let's say I start here, I travel to that point. Is that different? It's a great question. Is it at a different position? Yeah. What degree is that? Yeah. Okay, what about, I don't know, we'll put a triangle over here. Is that position different than the other two? Okay. Now I've gone how many degrees to the square? Okay. What happens if I go back to 360? Am I at a unique position? No. What about if I go, again, I loop around to here? If I do one circle, is it different at X? No. So there's some periodicity there that we have to keep in mind with our bound, right? So since our particle retraces itself, on a circle or a ring, it retraces its path after how many degrees will it retrace its path? Yep. What about radians? Yeah. Okay. So, keeping our bounds in mind. Remember when we were talking about particle in a box, it was like where the edges met. Here we could think about where our functions meet. What has to be true in relation to what we just said? If I want that to be true, what else do I have to tack in here? Yeah. If we're keeping in radians, which will operate in radians. So these two have to be equal to each other. Okay, we have a generic wave function, which I just told you the math was this, but I feel confident that you guys could figure that out. So AE to the I K phi is equal to what? So here we just are saying that, what's going to go over on the right? Yep. Okay. What could we do to simplify this to get to a result for a phi? Yep, we can divide through by A, and what's going to happen with A's? Yeah, that doesn't look any different. It doesn't look any better. Oh, well, we tried. So then we end up with correct? Okay, we can simplify this a bit further. What's another way we could express this right expression? We got e to the ikx, I'm sorry, ik, phi, yep. Yep, and that's all equal to this thing. So what would you do now? Yeah, you can multiply and combine them. Any ways you could simplify? Yeah, you can divide this guy over to the other side. And what are we going to get over here? Yep. Am I okay to write over here? So we get 1 is equal to ek 2 pi. Okay, this doesn't look like it's helped us to understand much right now. But what we're going to do now is apply Euler's theorem to this system. Euler's theorem states that e's, what functions can e to the whatever be broken down into? Yeah, sine and cosine. Everything can be described as sine and cosines or e's, which is cool. Fourier transforms for the win. Let's go to Euler's theorem. We got e to the I. I'm going to put theta is equal to cosine theta plus I sine theta. Does pink look different enough on the board? Or not really? Okay. I liked writing with this one. Let's plug in what we have. So we have e to the I 2 pi. This is equal to 1, because we showed it here. I'm back with our other expression. And now we also have this other stuff. So we're going to have cosine. What's going to go in the parentheses? And what else? Yep, 2 pi k plus I sine. What else goes in here? Yep. Okay. This has got to be equal to 1, or at least this bit here. Okay, what's weird about these two functions? This part, real or imaginary? Ooh, deep math philosophical question. This part's real. What about this part? Imaginary. Okay, we got a 1 here. Does 1 have an imaginary component? I would go with no. I'm sure there's some mathematician out there that's proved no, one has some blah, blah, blah. Here, where you're going to use practical math. We're going to get rid of that guy. So then, 1 has no imaginary term. Or component. So what we're going to say is then this portion might, or this portion here must have a value. This portion is just 0. See how well this erases. Okay. Boy, I was using pink. Therefore, cosine 2 pi k must be equal to 1. Okay. K. We got 2 pi here. It's got to be equal to 1. When's cosine equal to 1? 0, 2 pi, 4 pi. There's a quantization there. That's kind of what we always search for in quantum mechanics, or at least falls out of quantum mechanics, is that quantization. So there's a certain set of values here that you just said. So 2 pi k could be equal to 0. What else did you say, Lily? Yeah. Yeah. Okay. This gives us a hint that something has to be quantized in here. Where is the quantization hidden? It's hidden in K. So this means K must be quantized. And what values could K have? Has to be a whole number, so 0. Positive 1. Would negative 1 work? Yeah. Tell me the next set. Yeah. And we've had enough. Okay, so we have some quantization here. It's based off of the angular momentum, which is pretty cool. Using K, though, how many people want to utilize K as this new parameter we're coming up with? Anybody like it? Oh, okay, why don't you like it? That it's 100%, it is M sub L, and that's bugging you, but let's say you didn't know that. Yeah, we don't need more K's in our life. It's like how we need another like phi or an alpha or a beta. No, thank you. This is like one of the few times where I don't know in quantum physics who did this, but thank God they did do this. M sub L. I'm with you. I don't want another generic symbol that we have no idea what's going on with it. So this is M sub L. So now just as a quick aside, what quantum numbers have we found so far? N? Yep, and what are we missing? M sub. Yep. We're going to find these two with the next model systems we investigate, and then we'll have all the quantum numbers. This one comes out from a lot of experimental evidence, which we'll talk about, But at least now we have two that we can talk about. We're like almost to the way to the atom. Hooray! Okay, so therefore, our wave function that depends on phi, we still have our normalization constant that we haven't figured out, a, but what does the rest of this wave function look like? E to the what? Yep, m sub l. Sorry, that's messy. And what restrictions have we put on m sub l? Has to be a whole number. Negative numbers are included in whole numbers, correct? I don't think they are. I think whole numbers must be positive. Integers count, right? Yeah, yeah. Not all wootsits are a whatsit, but some whatsits are a woozits. It's like, I don't know. I'm with you, Lily. But I don't want Dr. Cox sitting out there staring through the window angrily at me. Okay, we got this. Ellen, you told me earlier that we have to do something. What have we not gotten to yet? We got to normalize it. So this is an unnormalized wave function. So now, to normalize. Okay. So we're going to figure out what A is. General normalization equation. When we normalize a function, what's the value over all possibilities, or all valid ranges? What's the value we should get out? Yep. What does the generic equation look like for normalization? Yeah. We're going to go even more generic. We're not going to include the n squared yet. Integral. Yep. Yep. Right, and where do our limits have to go before we start focusing in? Yeah. Yep. Okay, in our system, what are our integration limits? Yep, 0 to 2 pi. Okay, complex conjugate. A, E, how is our complex conjugate going to change this function? Yep. And what else goes in here? Yep. Okay, we're assuming the complex conjugate doesn't influence A. Then we just have a regular wave function. And what are we going to integrate over? Yep. Okay, simplify this a bit further for me. Still have our integration limits. Sure, okay. Sorry, I should have left more space. A squared comes out. What else are we left over with? E negative what? L phi times what? Yeah. Anybody see any ways we could simplify this? Yep. Can add these two guys. It ends up being e to the 0. What's e to the 0? Yes, best integral ever. How many people know how to solve that one? Yep. You just would look at the integration limit, so 2 pi minus 0, so what is it? Yep. Okay. And what's this all equal to again? Okay. What do we need to solve for? Yep. So get us a step closer. A squared is equal to what? Yep. Then what's a equal to? Yep. Okay. So we're at the last step. Therefore, what's our normalized wave function? Yeah. Yet again, 2 pi shows up over and over. So we're going to utilize this again when we talk about particle on a sphere, which is the next model we're going to consider. But not only there do we have to worry about m sub L, but we'll also have to worry about L. Then what we're going to do is take that model system and apply it to an atom, finally. Okay. So now we have a wave function. You could apply this back, a normalized wave function. You could apply this back to the Schrodinger equation, and it can be shown that the energy what were the possible values of m sub L again? 0, plus or minus 1, plus or minus 2. Okay. Hint before you go on Easter break, Easter gift. That's why I'm wearing purple today. It can be shown. What do you think one of your Quizlet questions is going to be? Work that out. Okay, what other things does this tell us, though, about angular momentum in quantum particles? What does it tell us about angular momentum? At least for quantum particles. What's the difference between classical physics and quantum mechanics again? No, that's actually the most concise and perfect explanation. Yeah, it's quantized. So what does it show angular momentum is? When we can only have discrete values of m sub l and the rest of the things are constants. Yeah, it's quantized. That's a big deal because does that happen in classical physics? No, it doesn't. So it's really, really strange. We use this to our advantage when you talk about NMR, because there are only certain states that the nuclei can spin in. Rotational and certain vibrational spectroscopies, this makes a big deal with too. So the reason some of those spectroscopies work is based upon this quantization. If you didn't have those levels, when you hit something with radiation, you would have no idea what's happening because it would be a continuum. In quantum particles, such as molecules or atoms, that's why this thing works out, because there's discrete values for it. Okay. Are there any questions about the wave function, normalizing it, anything about particle on a ring right now? Okay, we have about 10-ish minutes left. Let's draw some pictures. After we draw some pictures, we'll be done for the day. We're gonna start art class. Am I okay to erase this thing? Cool. For this next bit, you'll wanna give yourself about a full page to make this table. I'm going to try my best, and hopefully the colors are different enough. What we're going to do, we're going to be plotting the wave function. My favorite animation has gone offline, so I'll try to find a new one so you can visualize this. It came off of a physics website in the past. What we're going to do is we're going to plot different values of m sub l. How do you spell circular? Oh God, that looks so bad. Anyways, we'll draw a circular representation, and you'll see what that means in a minute. And then we're going to have a linear representation. Okay, the circular representation, we're going to try to draw the wave function as it boops around on that ring. The linear, we're going to like pull that circle apart at the boundary of 0 to 2 pi, and we're going to slap it on a 2D plane. Does that make sense to people? Okay, if you get confused, say so. If something visually doesn't look right, or you can't tell the difference, say so, especially with this crappy chalk. That's the last time I'll bring up the crappy chalk, because we have 10 minutes left. All right, let's look at an ML of 0. This one is the most boring one by far. What we're going to do is we're going to draw our circular representation. And we're going to try and show, so if this is the circle, I'm trying to bend it at an angle like that so you can just sort of get an idea of depth. So this goes in and out of the plane of the board a little bit like this paper right now. Okay. We're going to try to show positive and negative of the wave function. So anything that goes beneath here and these lines along there, that would be considered negative. The other would be positive. Okay, so now if we look at our wave function, normalized wave function. That's what we have, right? If m sub l is 0, what happens? Yeah. Does it depend on what phi is? So if I change this number here, is it going to matter? What's the whole exponent going to be? 0. So it's always going to be 1 over 2 pi. This is a boring one. What this looks like is the wave function's just literally a circle. And what is the maximum of that value? One over what? Yeah. Square root of 2 pi. Now, if we take that circle and we break it apart and we stretch it out in a linear fashion. So in this point, we're going from 0, pi, okay, on this circle, let's say that this is 0. Where's pi? Over here, right? And then where would 2 pi be? Back to there. Okay. We have a maximum value. What's the maximum value of this wave function? Yep. Okay, and what does it look like? Does it change? Nope, just goes, that's meant to be a straight line all the way to 2 pi. Uneventful. Let's look at it. We have plus or minus 1. I'm going to shift that down a little bit. Okay, same sort of thing. We have a circle. I'm going to tilt it a little bit. Oh my God. Try that again. Do you guys ever watch those videos of people who like do those weird arm movements and they have competitions about making the most perfect circle? Okay, I'm not the only one, thank God. Like, if you have to have a skill to have, it is insanely impressive, but it is completely pointless. Like, but I still want it. Okay. Now let's think about what's going to happen with this one. So we could have plus or minus up here. It's not going to impact it a ton because it's a periodic function. So let's just consider plus. What will end up happening? Which side did we pick to be 0? Okay, so we picked this side to be a 0. We're starting on that side. What will happen is we should get to a point where we just go kind of linear along there, and then it zips down that way. Linear, and it comes back up. That doesn't look helpful on a 3D plane at all. Let's plot it out as a linear representation. Zero, pi, 2 pi. Okay, again, the maximum value we can have, what will the maximum value be? Yep, and what will the minimum value be? Yep. Okay. where will the maximum occur? Or where will it be close to of these points? Yep. My alarm. Actually, it's a pharmacist calling me to complain about Lydia's medicine, and then farm telling him to shut up soon. I'm sorry, Ellen, can you repeat that again? Yep, 0, we're at a maximum, and it starts to shift which way as we move to pi? Down, yep. And then what happens as we go from pi back to 2 pi? Yep. Okay. We don't really have enough time to draw out plus or minus 2, but what do you think that's going to look like? Yeah, it's just going to get more squiggles in there. So we're going to add more squiggles each time we increase that m sub l. It will change where this thing dips and goes up. That's at least what the wave function will look like. What I'll try to do over break is find a new animation that works better so you can see those things and actually control the value of m sub l, and you can see how it changes and impacts these other things. Now, let's say I were to, this is the plot of the wave function. What would the electron density look like? Yep, just jumps up. How many nodes are in this system? Okay. I'm satisfied with that. So what we talked about this class is we determined what the wave functions are for a particle on a ring. We normalized them. We figured out, plotting them, what did they look like? Are there any questions about that? No? Okay, next time what we're going to talk about is degeneracy. When it comes to, what does being degenerate mean again? Yep, exactly. We're going to explore that when it comes to particle on a ring. After we do that, then we're going to move to particle on a sphere, and we're going to see a change there. Then we're going to take that information and combine it with something that isn't necessarily stuck on a sphere. It can move in any direction along our R component, and that's finally going to get us to atoms. Okay, the math gets complicated there, but we're going to find tricks to get around that. All right, are there any questions about particle on a ring? You have a daily problem, but what else should you be prepared for on the exam? Yeah, you got to show me how do you get that energy expression. Okay? No other questions? All right, have an awesome break.